Get in there, get in there, get in there. Okay. All right. Hello, everybody. This is CH10, and for the Silicon Valley FIG, the March meeting. Okay. This morning, I'm going to talk about not forth, a little bit of chemistry, a lot of thermodynamics, and it's about the cubic Vera equation of state. Okay, it's a long story, but I think I do have some time. In 1972, while I was still a chemist, teaching in Taiwan, and you know, 1972, that's in the United States, the mini computer revolution is raging. So in Taiwan, we got kind of at the end of the wave. But I was in the chemistry department, and in the same building, we have a physics department. And so we always share our toys. So one day, my assistant came over and said, "Oh, the physicists, they got a new toy." Okay, so we went out and see what it was. And if you guys remember N1 or N1, so the N1 was an engineer with IBM. And one day he got that big idea, so he quit and started his own company. So he got sued by IBM. And he's not very happy, so he countersued. And he actually won. And got I don't know how much money he got, but he got some money. So he started an N1 company. And he specialized in office automation. And actually, he was building mini computers, as we know it. But he devoted himself mostly on the office equipment. So he was quite successful. And so we got one of his machines. And it's a desktop computer. But it's not a desk computer by look. It looks just like an IBM daisy wheel printer, I mean the typewriter. But it got a long cartridge, and the cartridge can print paper, and it can print graphics. So that was a very interesting thing. I think it speaks basic or something like basic. So you can actually type in commands and get it to do something, okay? And because you got a big cartridge, and you can print lots of things out, and you can actually print and doing graphics, okay? So we were thinking, oh, what are we going to do with this thing? The physicists, they didn't know what to do with it, but everybody's kind of like it to try their hands on it. So I said, well, okay. At the time, I was thinking of doing the gas, liquid, solid equilibrium. And I think I need some good graphic printout. And at the time, the computing center was in another campus, and it's kind of awkward to go there. And the printing facility was, you know, just a regular printer. So you got characters, but not very interesting. But this one can print dots. So we got it to print out some graphs. And so I wrote a little paper on how to evaluate the gas, liquid, and solid equilibrium. But that was based on the van der Waals equation. And I was not very happy with it because the van der Waals equation has kind of limited you you cannot go very deep into the high density part of the graph. So that was put, we published it in the journal of the school. And I think it never get outside the door of the school. but it's in 1972. In English. So I had a big idea about this gas, liquid, solid equilibrium. At the time, it's not a well thought out, and because I don't have a very good graphic capability, so I cannot do too many experiments. But get back to the equation of state. Equations of state, these are functional relationships among pressure, volume, and temperature of gases, okay? So in the scientific revolution, the study of gases were one of the pillars of the scientific revolution. And in 1662, Boyer did an experiment, and he found that the PV, for any gas, the volume and the pressure, the product is a constant. So if you increase pressure, you reduce the volume. If you reduce pressure, you increase the volume. And then in 1787, Charles came out with this equation. He's studying volume and temperature, and he found that the volume increases with temperature. And in 1834, these two laws were combined to become the ideal gas law. So PV equals to nRT. So this was the understanding of gas at the time. But this is the ideal gas. They knew that the real gases are different. But at the high temperature, at large volume, all gases behave this way, okay? But yes.
You know the difference between ideal and real.
Yes, yes.
Like the molecules in an ideal gas do not interact with one another.
Right, right. Mm-hmm. Yeah. And the molecule does not have volume. They are points, okay? And the real gases behave differently from ideal gas. And so one of the first things that happened was Van der Waals. In 1873, he wrote his PhD thesis and put down this equation. And so this is called the Van der Waals equation. And he said, well, you know, the real gases, the molecules have volume. And so this free volume has to be the real volume subtracted off the volume that occupy the molecules. Okay? So this ideal gas equation has to be modified this way. And another thing is that molecules, if they are far away, they do not interact. But when they are close together, they have attraction. Okay, and this actually this A, if we write this way, A is minus, and it shows that the attraction of among molecules. So molecules has repulsion when they are getting real close, but they are close enough but not very close. They have attraction. So with these modifications, he can account for lots of properties in real gas, and he can actually divide this from this equation. He can explain mathematically the existence, the coexistence of gas and the liquid. Okay, and so this equation it is qualitatively significant, but quantitatively not very accurate. So there's lots of modifications introduced into this equation so that the data would fit experimental data a bit closer. So there's these modifications. And over the years, lots of equation of state are basically modifications of Van der Waals equation. Yes.
Especially in astronomy or astrophysics,
Mm-hmm.
when you do stellar models, you have to use an equation of state. And those are very complicated.
Yeah.
You get down into the core of a star.
Yeah. When you are, I think when you are dealing with gases at very high temperature and a very high pressure, you know, they have a strong.
Also, if they're nuclear,
And these are more fiction than science. Okay. Okay, so these modern equation of state are still based upon equation of the Van der Waals equation, but with a lot more corrections thrown in so that they can fit data more closely. And of course, there are equations of state which is not based on Van der Waals equation, because Van der Waals equation has the fundamental problem that it has a singularity at the v equals to b. Okay, it you know the underside v minus b becomes 0, and the equation blows up. Okay, so there are other equation of state, and this is the original Vera equation by Camping Owens. And here, the guys which do the Vera equations basically they seek numerical accuracy. So they want to represent their experiment data accurately. So they just expand, use many terms, use the Vera equation. And if you include enough terms, and if you include temperature dependence into the Vera coefficients, and you make enough terms in the temperature dependence, you can get really close. Okay. And then the Bridgman, Beatty-Bridgman equation of state. This looks like the Vera equation, but it is a kind of Van der Waals equation. But he just turned this v minus b underneath in the denominator by v plus b. Okay, that was very clever, and it get rid of that singularity. And there are other things which are complicated beyond comprehension, as I say here. So Van der Waals equation of state has a singular point at the v equals to b, and it does not allow investigation into the region of v less than b, and that's where solid state is. Okay, so the Van der Waals equation is not adequate. If you want to go down to the high pressure, small volume area, high density region. And non-Van der Waals equation of state are generally completely beyond comprehension, because when you seek numeric accuracy, you introduce more terms, and basically you cannot give physical meanings to those coefficients. Okay, so one of these. In one of my sleepless nights, came out saying, well, you know, if we just take the zero equation and truncate it, so we only keep 3 terms, and this equation can be solved quite exactly numerically, and it has all the nice properties of Van der Waals equation of state, but without the singularity. Okay, so this, of course, the reason why people take many terms in the real equation is to seek numeric accuracy. If you truncate at the 3rd term, you cannot get things to be very precise. But there's lots of properties in the gas-liquid equilibrium can be represented quite satisfactorily with this equation. Okay. Okay. Generally, what they treat the equation of state is to use the data at the critical point. The critical point of a gas is that at a certain temperature, pressure, and volume, the liquid becomes translucent. Okay. Usually, it is if at a high temperature, it's gas, transparent. At low pressure, it's liquid, it's still transparent. But in between the gas and gaseous state and the liquid state, there is a very narrow region that the all material, all gases behave this way. At the critical point, the gases and phase and the liquid phase kind of coexisted, and so the whole thing becomes milky because the 2 phases are intermixed and cannot be clearly separated. So at the critical point, if you take the P, V, and T curves, and it's the derivative, the first derivative of P against V and the second derivative of P against V are both 0. So here, we have P, we have V, and for ideal gas, this PV equals nRT, generate this curve, this T, T1, T2, T3, and when the temperature is higher, the curve goes up. But when you have V equals to RT, V minus B minus A, B square. So this term gives a negative trend to the curve. And this term at V equals to B, it can increase to infinity. So it has this correction curve. And if you superpose these T curves onto this curve, then at a certain point, this thing becomes this way. And at the critical point, you see here, generally you can find 3 roots in this curve. And when these 3 roots collapse into 1, and that's the critical point. And at the critical point, if you take your whatever the P equals to a PVT equation, right? And if you take the derivatives and insist that the first derivative and second derivative are zeros, and you can solve for A and B, or any of the parameters that you throw in the equation. Okay, So the cubic Vira equation, if you use the conditions, impose the condition that the first derivative, second derivative of t against v has to be 0, then b can be solved to be vc, and the c equal to vc squared. Actually, I'm sorry, this is it has the RT in front of it. It has the RT. So this equation, generally, if you use the critical point property to scale the temperature, pressure, and volume, then you get a reduced equation of state. When you use P equal to the scale the pressure by the critical pressure, scale the volume by the critical volume, and scale the T by critical temperature, then the equation, all the parameters disappeared. Okay, and you had this called reduced EOS. Very simple question, very simple equation, and very easy to plot. And I think that I'm pretty happy with in doing it, because in F#, I got a great graphics engine. Okay, I can plot anything. Okay, and here, if you use reduced equation of state, P, T, and V are all very close to unity. Okay, and when it's very easy to plot out, because it's scaled automatically, and it fits your graph very nicely. Okay, all right. Here is a nice plot, and if you Google the real gas or Z plot, and generally you'll find this picture. And this picture is interesting in that it is consolidated 10 different molecules, 10 different compounds, or 10 different gases, and plot their properties in reduced scale. And you can see the Z is PV equals PV divided by RT. If you remember the ideal gas law, PV equals to nRT. Okay, assuming n equal to 1, then PV divided by RT generally is 1. Okay, and for real gas, the Z plot deviates from 1. So if you can see, the 1 is on the second line on the top. And then all these gases are very different molecules. But if you use their measure their pressure and volume at certain temperatures, and convert all this data into the reduced parameters, and they all follow same lines. For a particular temperature, they all fall into the same line. So this is a nice test bed for any equation of state. If you do any equation of state, you have to be able to reproduce this plot in order to claim any usefulness. So I took my cubic Vira equation of state and plotted. Well, it has the general shape, but not very good. And at temperature, and these are too low. The Z value is too low. Let me go back to this. See here, they kind of spread out quite evenly. But in my plot, I kind of get together at the low side. No problem. So the cubic Wheeler equation needs to be scared because they tend to be too low. So increasing the temperature, these coefficients should be getting smaller and smaller so that they can get closer to the z equal to 1 line. And okay, obvious all the lines are too low. And so we need, if we reduce this this term by dividing it by t squared, then it raises these curves towards 1. Okay, so I tried t squared, t cubed, and all the values, and found, well, t squared looks the best. Okay, so here, you see this plot is very close to the experimental z plot. Okay, so if we correct the second and third Wheeler terms by a factor of t squared, inverted. Okay, so I think this is a quite nice. The plotted value corrected by t square factor, it generally comes to 5% of the real value. So it is pretty good with only 2 parameters and that correction, that t square correction. Okay, so that's I think for the gas. The z plot is basically all the data above critical temperature. Okay, so that's pure gas phases. All the gases are in the gas phase and they behave quite nicely. All the equation of state behave very nicely. Now let's consider consider the gas-liquid equilibrium. Okay, and so this is the general picture of gas and the equilibrium between gas and the liquid. So if you correct the ideal gas by a function similar to this, you can generate it with different ways. Van der Waals is one way. The cubic Wheeler equation of mine is another way. They also are corrected by shape like this. And this correction pull down the PV isotherm so that it has a S-shaped band. Okay. And this is very important because this S-shaped band accounts for the coexistence of 2 different phases. Why? It is very interesting in that, in this region, that dP dV, the slope of this curve is positive. And in this region, the slopes are negative. And in thermodynamics, for stability, this dP dV has to less than 0. This is the condition for stability. Actually, intuitively, it's also very obvious because here, if you increase the pressure, you should, if the pressure increases, volume also increases. That's unreasonable. Okay, weird. So increase the volume, then increase the pressure, the volume has to decrease. Okay, so this is obvious because everyday experience tells you that if you anything you press on it, it gets smaller. Okay, so these portions are stable, and this portion is not stable, because if you increase the pressure, the volume gets bigger. When the volume gets bigger, the pressure increases more, and volume gets even bigger. And you go other way too. Okay, if you're getting smaller, things getting smaller.
Does that occur in nature, or is that just a manifestation of an inaccurate?
This is the stability, the condition of stability. So it is physically or thermodynamically, that's a true statement. Okay. So if you you can plot anything.
You have an unstable material, right?
You have an unstable state.
Yes.
Okay.
That means you have two phases.
Yes, and the nature in this unstable state, what does nature do? It separates into two different phases. And so actually, when you're at a certain temperature, when the volume increases, the pressure decreases. Okay, and at this point, it jumps. So here at this point, it jumps into the equilibrium. And at this point, when all the material turns into gas, and then it follows this piece. Okay.
So that's like the definition of boiling point.
Um,
Got a liquid that's following this line. We get to that certain.
yeah, it's
Then it tips over and becomes a gas.
yeah,
So
yeah,
that would sound like a boiling point.
yeah, right.
So,
Yes.
so, I'm sorry.
Yes, go ahead.
This is not with the addition of heat. This is when you arrive at this place.
Yeah.
Mhm.
Powerful in transition.
Exactly.
Yeah.
And you're getting into an area where it becomes unstable and
Yes.
it's switched over to another.
Yes, yeah.
And I was going to say that one of the things that popped into my mind, no pun intended, is that this mechanism here seems to call to mind a quantum tunneling diode. There's that point where you have that point of negative resistance. And a lot of times people have applications come from that. I'm curious to know if we have anything in the chemical world where we actually exploit that bit of.
Oh well, we use it all the time. Yeah. Okay.
I know what you're talking about. It's,
Another term is catastrophe.
yeah.
Okay, when the state becomes unstable, and catastrophe has to happen, and that catastrophe in here it is the material separated into two different phases.
Okay.
Yes.
I remember there's a new type of dry clean method using a liquid that's in this funny state that when you saturate, whatever you're cleaning, and then you change like the pressure, that catastrophe you're talking about rolls out all the dirt out of the cleaning.
No. I think the cleaning is that I think they use some material where the liquid phase, the gas phase and the liquid phase is so close that you can turn the it's just normally it's gas, but at certain pressure it becomes liquid, and when it's liquid you can dissolve all the oil into it,
Right.
and then it takes all the oil out of the cloth. Okay. Generally, I think how do you clean the PC printed circuit board before you do the photograph and etching? Okay, what you do is using carbon tetrachloride. Carbon tetrachloride is very heavy, and it's liquid, but it's very heavy. And if you take a big, 50-gallon tank and put some carbon tetrachloride at the bottom and heat it up, it will boil. So the gas would rise. And if you put a piece of printed circuit board there, because it is cold, and the gas condenses on it, and then flow down, and that bring down all the oil.
Yes.
So
I remember that back.
Yeah, dry cleaning. I think many of the dry cleaning methods are based on this principle. Okay. So this condition is called a level rule. Where do you have to draw this line? And to draw this line, the condition is that these two areas are equal. Okay. So if these two areas equal, and then the gas and liquid would take this pressure as its saturation pressure. Okay, it's kind of, yeah.
This is from a material scientist, I think, sort of in this building. When you have eutectic diagrams, you have free energies and stuff. When you have two phases, you look at things. I don't remember the details, but you come across it. And that whole eutectic thing where you have a stable flat line.
Yeah.
It's the fact that you have fractions.
Yeah. Right.
Both
Right.
sides.
Yeah. Yeah.
Yeah. It's a very familiar type of phenomenon.
That's right. And mathematically, you can find out this condition precisely by the free energy, by calculating the free energy. Okay, and this is the equation I'm putting down here. Not in details, but it's the Gibbs free energy, which control the behavior of material under constant temperature and pressure. Okay. So.
But that's one more thing.
Yes.
So if you have a system that is following that curve where you have
Yes.
that S band,
Yes.
that really means that you're going to get to a point where the P pressure, let's say you're reducing P, in fact, you've even got an arrow, you're going down on that curve, you're going to hit a certain point, and then the volume is going to transition. As you reduce the pressure further, the pressure will stop at a certain point, and then you'll have this, on that line, you go from the left side of the line to the right side,
yes.
and then continue down.
Yeah, that's right, that's right. And that's, at this point, the Gibbs free energy is constant, okay? So the Gibbs free energy, it's kind of, I don't want to go into the thermodynamics too much, but it's just in the last chapter of the thermodynamics, you get this G, okay? And the G at the constant temperature, delta G is equal to V dP, okay? So if you integrate VdP, you get the Gibbs free energy. But you can see here, our equation of state is a P as a function of V and T. So the P is so VdP is very difficult to calculate. Okay. Because you have to invert this equation into the V as a function of P, then you can use the equation. But you see, VdP is equal to dP. Okay. Actually, the real equation is dG equals to S dt plus V dp. Okay, so this is the fundamental relationship of Gibbs free energy with entropy and volume. So if you're at the constant temperature, and then the dG equals to V dp, and if you integrate this one, and you get a G equal to V dp. Okay, and the V dp is actually, sorry. So dG equal to V dp. And I think I better not do the thermodynamics now. Just take my word for it. Okay. Yes. PV. If you VdP equals to dG minus PdV. Okay. And if you integrate both of them, you get a PV and this part. Okay. This part can be done analytically or graphically. Okay. Because I have a great graphic engine, I'll just do it graphically. Okay. And do it graphically, the G, if you plot against the P, you see here, you follow this curve, and PdV, VdP, it is this area, okay? So you when you integrate, you follow this curve and integrate this part, okay? And going down here and going up here, this is making a curve like this. So here the VdP decreases to this point, and then after here it increases, and after that it decreases. And when it at this point and this point they cross. Okay, so from the graphics, it's very clearly, you know, this G curves make an inverted 4, like a 4-character inverted, and you just look for this crossing, and this crossing at the pressure of the saturation pressure. Okay, so that's you know, that equation, the cubic Wheeler equation is simple enough. I think you can do it analytically. But since I have since I can plot them easily, I just do the plotting. Okay, and with this, this is the original reduced equation of state. I try to plot this one. The result is not very good. So I try to scale it with t and t square, and t is pretty good for a small region, and t square gets too big. Okay, so I can see that the best result is in between these two, and I use the t scale it by square root of t. And this one gets a very good result. Not perfect, but very close. So I have plotted everything many times until I decide, well, equation 12 is the one I want, or the best I can do. Okay, I plot equation 7, equation 12. This is original cubic equation, scaled by t and scaled by square root of t. So you can see here for this free temperature, and the equation 13 is very good. You know, it agrees with the experiment almost perfectly. But when you reduce it to a lower temperature, it doesn't, the G curve doesn't cross anymore. Okay, the curve are too low, and the G does not cross. So so you can only use it to this point. But if you reduce it scale by a factor of square root of t, and it generally has a very good behavior. And at this point, under here, it is below the triple point. So it, the solid state can be. But for the coexistence, the equilibrium between gaseous phase and liquid phase, this seems to give the best result, overall result. So the best result is equation 12. So here I'm plotting the equation 12. You see here, these plots are the G and the Gibbs free energy. You can see if you go down with high temperature, the curve goes down and follows the curve. When it comes down here, this Gibbs energy comes down here. And then the curve goes up, so Gibbs free energy goes up, and until it it hits the top, then it goes back down and make a cross. And at the crossing point, that's the saturation pressure. And if you set at the saturation pressure, if you draw a horizontal line when it crosses this PNV isotherm, and you can find that the volume of liquid. If you go to the to right, well, it's off scale. So it can the gaseous volume is so big, you cannot see on this graph. So this gives a very good. If you scale this cubic equations properly, I mean, then it can account for the behavior of gases between the critical point and the triple point. Yes.
The triple point is the temperature where gas, liquid, and solid are
Can coexist. Okay. Yeah, just 1 point there. Just like a zero at 0 degree, ice, water, and steam are in equilibrium.
water vapor, right?
Yeah. Okay, so that's what I'm interested. Okay. I'm thinking, okay, if by introduce this this correction in the P in the pressure curve, we can produce an S-shaped bend, and this bend accounts for a new phase, a liquid phase. Now, if I can bend it again, I should be able to get the solid phase, right? If you somehow introduce another bend, and then we can have one more phase, and that's solid phase. If we introduce a bend, something like this, if the correction here, I can do a correction like this, okay, with a very sharp bend. and superpose this one on the PV curves. We should be able to get the curves like this. And then, you know, this will be the equilibrium between solid and liquid. And this will be the equilibrium between liquid and gas. And at certain point, these two pressure becomes the same. And that's the triple point. Okay? So, with my cubic equation, I can introduce this band mathematically. Okay? So, this cubic equation, if you multiply by these three, it's basically a cubic equation in V, and the cubic equation in V has three roots: a certain temperature, certain pressure, okay, and this one accounts for the coexistence of gas and liquid phase. Now, if I can introduce another band at the proper volume, I should be able to introduce the solid phase. And actually, I knew the roots that I have to introduce into this curve. And so here we can, you see this equation up to this point, and that's my Weir equation. Okay. And if I add two more terms, and I introduce two roots at Vm and Vl. If I introduce these two roots, and this equation is a fifth order equation. And the fifth order equation should have 5 roots, okay? And the 5 roots, 2 of them already, 1 of them a gas, a liquid, and a solid. And 2 roots are in an unstable state, okay, in between gaseous phase and liquid phase, and also 1 between solid and liquid phase. So you see, I've already Vs in solving the cubic Weir equation. I've already got Vs. Vs is 1/3 of the critical temperature, and that's where real gases have their solid phase also. So I've already got this root, and if I add 2 more roots there, I got my equation of state with a solid phase.
So I wasn't following all.
Okay, okay.
You've got several roots, right?
Yes, yes.
And one of the roots,
Okay, here.
One of the roots represents a triple point.
Here. Let me go back there. Here. So if I introduce a band, an S-shaped band, in this region, in the solid and the liquid region, okay, and I bend the curve this way, okay, and this, if you remember the level rule, if I draw a line and these 2 areas equal, then these are 2 different phases, and in this region, this is a solid phase, and this is the liquid phase.
Okay. So
the other roots. Yeah, if it usually is at a lower temperature. We got 3 roots, and this root is liquid, and this root is gaseous phase. Okay, and this the root in the middle. This represents the unstable state. Okay, so when this, if I lower the temperature, this one will be lowered faster than this level, okay? And when they meet, when at a certain temperature, these 2 levels are equal. And that's where I have a solid, liquid, and gaseous phase, okay? So this is the condition that I'm looking for. So when I'm correcting my, I will hope to get an equation which can have 5 roots at certain pressure at the saturation pressure of the triple point. At that point, if I can produce 5 roots, then I got the solid the 3-phase equilibrium. So I'm plotting it, expecting to have 5 roots, and the result of the plot is this. It looks awful, but I do have 3 roots. I do have here. I do have 3 roots at VS, VM, and VL, but they are so close and that they are so shallow that on this graph you can see only a flat line. But if you really blow it up, you can see the S band. Okay, so this is unsatisfactory, and the cubic Weyl equation need this kind of shape to produce the triple point, to produce the critical point conditions. And now this one, because of the added terms, so this curve gets raised quite a bit higher. So the critical condition is completely out of range. Okay? And this, although I have 3 roots there, 3 roots are so shallow that if you raise the temperature a little bit, the temperature, you know, that PV equals RT, this curve will pull this this S-shaped band straight, and you will not have just above a little bit above the absolute 0 temperature. The root disappeared. Okay, so this equation is not. It has theoretically the kind of shape, but it does not. It cannot account for the existence of solid phase, because we know solid phase and liquid phase exist along a very wide temperature range and temperature pressure range. Okay, so you. Oh, and that's okay. Thank you. Thank you. So we this equation is not satisfactory, but how to correct it? I think I want to keep the 3 roots. Okay, I still want the solid phase and the liquid phase in that very narrow range. So these roots. Okay. So here, these are the VM and VL are the roots, and the VS is the already we have it. So what we can do is to raise these 2 terms to a high power, and this will instead of very shallow S curve, it will increase the steepness, or the height and the depth of this S band. So what I can do is to raise these 2 terms to very high power, and then look for the correct behavior of this curve. Okay, so how many? What's the power that we need? So n equal to 1, that was the shape, the curve that I showed you before, very shallow. And n equal to 2, 4, 8, 16, 32. And at the n to the 16th power, you see here, this is the n to the 16th. So it is not quite large enough. But n to the 32 is way big, way too big. So I knew from looking at this curve, I knew the correct power is between 16 and 32. Okay, so I just go and look for it. And the best curve was generated when n equals 26. So if you raise these two terms to 26 power, I got the right isotherm. And the triple point for argon, the triple point is at half of the critical point. Okay. The pressure is very low, almost close to 0. And Vs, that's the solid phase, the liquid phase, and M, I don't know. But that N is must be between S and L. So I might just well take the midpoint of it. Okay. So these are the parameters that are used, and with power to 26 power, and this is the curve I'm looking for. So here, this is the Gibbs free energy curve. So I'm plotting the critical point curve just for reference. Okay, and actually this curve is the n to the n to the 26 at the temperature of 0.553. That's the critical point. What I'm expecting is that this Gibbs free energy from here down. So I got that straight line there, and coming back, following this curve up to here. So this up to here, and when it drops down, the Gibbs energy also drops down, down to this point where it crosses this one. And this is close to P equals to 0. And because at the triple point, the vapor pressure is very low, and it's all, for all practical purposes, it is a 0. So if this crosses at 0, then I get the right end. So in the when I'm testing from 16 to 32, I'm testing everyone, and so this crossing point for 16 is way up there. And then if I increase the n, the crossing becomes lower and lower. And at the 26, it has become 0. And that's where the triple point should be. Well, taking this, I wasn't, when I started, I wasn't quite sure that I can actually raise this into the 26 power. And because I was only using the 32-bit integer. All the thing was done in 32-bit integer. Of course, I have my I have all the tools to do the floating point coprocessor. So anytime if this thing doesn't work, I will switch to the floating point coprocessor. But since it worked all the way to 32nd power, wow, I was so pleased. And actually, I tried the 64th, and it still worked. So the scaling, when you do raising the power, if you scale these quantities properly, if you scale the V and Vn properly and keep in a reasonable range, and these terms would keep in range. Okay, and but if I noticed that if I go too low in volume, it blows up. Okay, the F sharp just quit. Okay, so here we have this equation is the proper equation to account for gas, liquid, and solid equilibrium. This part, I think the battery probably is not. This part, okay, is the cubic Wheeler equation, and in the volume close to critical point, these two terms doesn't contribute anything. So the gas liquid equilibrium can be accounted for. Okay, as I showed with this just a cubic equation. But if we put in these things and throw in a big bang in this region, and then we can have explain the triple point very nicely. Okay, conclusion. The cubic Wheeler equation has all the nice properties of van der Waals equation without the parametric singular point. And this cubic Wheeler equation can be modified to this form, and it can account for the coexistence of gaseous, liquid, and solid phases. Okay. Yeah, you go ahead.
What is it about real materials that make all this variation? Are there like geometry popping in and out of each other?
Well, the equation of state really doesn't account for what molecules really do, but globally or macroscopically, they describe the behavior of material when you have lots of molecules in it. So these thermodynamics is about the macroscopic behavior of molecules. But so far, the microscopic view of the material kind of leads to the same macroscopic equation of state.
It's kind of like, you've seen that thing where you have this glass tube, there's a little bit of, say, like cotton in it, and there's a plunger, and you suddenly press the plunger down, the cotton ignites. Right, but let's assume that this cylinder is it doesn't let energy out. It's a perfect insulator.
Yeah.
And if you were to slowly press the thing down, what will happen is the cotton will ignite. That's because the fact that air is a real gas. What happens is when you start getting into those densities, the molecules start bumping into one another, and they start exchanging energy. It could be from rotational or vibrational, because oxygen is diatomic.
Yeah, this is adiabatic. Adiabatic. Yeah. When you have adiabatic process, when the energy doesn't escape, then you can raise the temperature real high to ignite it.
You notice that molecules have a spectrum. Now, if they're, I think it's, what is it, rotational is like in radio waves. Vibrational is like
in the infrared.
And that kind of thing. Then you can get up to the thing where you get the actual electrons jumping orbitally.
Yeah.
And that's usually visible to the audience.
Okay. Any other comments?
Oh, this is great. I wish I could read this. This is cool.
Okay. Yeah. I think astronomers are very interested in the equation of state.
Oh, yes. Yeah.
You send your slides to David for the meeting notes?
Yeah, sure. Yeah.
So when you have an equation with singularity, in material science, you get a lot of that, where you get this thing where, especially dislocation theory, where you use continuum mechanics, you get too close to the atom, the whole thing breaks apart.
No. In reality, it doesn't happen.
So you're dropping terms. You're basically almost doing a Taylor expansion of the singularity,
yes.
and throwing away the thing.
Oh, yes.
You could have looked at
Fit-
the numerical accuracy of your machine and just had a cutoff and said, if you divide by 0, let's get the smallest.
Yeah.
Yeah.
It's a.
Basically what you're saying, let's not go there.
Yes, the singularity physically does not exist.
Yes.
Okay, so that's the problem with the van der Waals equation. Okay, because physically there's no singularity in that region. Okay, so the equation is wrong.
There's actually another term that if you were to take into account the actual size of those little, it'd be ugly, but it would do it.
No, it's just that the van der Waals equation is not accurate. It's wrong. Okay, you shouldn't use it because singularity is does not present in it.
There's another thing. If you go back to your first slide, can they hear me, or we can repeat this?
Yeah.
I could go to a speaker if necessary. If you go back to your first slide when we were going to Boyle's law with the dates. Okay.
So if you could just go stand next to it.
Okay.
So that
Yeah.
everybody can hear it.
Okay. Okay. So the question I have is, in 1662. Okay. So we have Boyle's law, we have Charles' law.
Limit to your clothing, please.
Okay. We're learning. Okay, can we hear? So it took 100 years to go from Boyle's law to Charles' law. The question I would have is, it took another almost 50 years before people took two equations, which are very simple linear equations with some similar terms, and decided to combine them. Why did it take 50 years for somebody to discover the ideal gas law? To me, it almost sits there saying, hey. So that's just my observation.
Well, I think in the early days, people kind of skeptic about all these laws. Okay, and it's not obvious that nature behaves in a way that you can write the mathematical equations to it. Only until Newton came out with his big book, the mathematical principle of natural philosophy. Okay. At that time, there's no science. Science was not invented yet. So what was science? That was called natural philosophy. And so he laid down that the nature actually obeys mathematical laws. Wow.
Could I ask you to stop and clip the mic to the whole thing, please?
Okay.
Don't unclip it until you're done.
All right. So I think it took a long time for science to advance. Yeah, and it has all the various things that contribute to the progress until we finally understand how what the most gases behave. Yeah. Mm-hmm.
It's interesting because I remember seeing a screensaver where it showed these bouncing balls that were using that equation of state where when the balls were far away from one another, they were attractive. But when they got close together, then it was repulsive.
Yeah.
Yes, that was a more of a more real, instead of ideal, it was using
That's right.
real.
Yeah. That.
Lorentz attractor?
No, Lorentz attractor is a mathematical.
So I think you see here, Van der Waals want to explain this thing in his equation. Here's the attraction term, and here is the repulsion term. But he expressed the repulsion term in such a way that it's mathematically ugly and not quite good for reality. So here, this equation has a very nice property that here this term is the kinetic energy, the gas molecules move, and this term is the attraction, and this term is the repulsion. So it expressed this very clearly, mathematically, very clean, and I think in reality, if you kind of making some corrections to these Vieira terms, you can actually account for very good for the experimental results. Okay, thank you very much. Yeah.
Chang, you should make a series of all your papers that you've done.
Am I on? Right. All righty. We've had a fun month in Fourth Haiku, and I thought I'd share with you some of the goings on. So the first current event was our storm of spam. If any of you happen to visit the Fourth Haiku site this month, you saw a number of haikus that look a lot like this one. Oh, come on. Tap. You'll notice that it's magenta. Magenta's lovely and all, but it's magenta because it's an invalid haiku. Magenta is Fourth Haiku for that does not compute. Some marvelous spammer on the internet discovered Fourth Haiku. I'm not quite sure. I think what they're doing is probing for escaping vulnerabilities. They're attempting to inject various URLs and patterns. For a span of time, they were dropping down, dozens of them per minute, and then they would go away for a while and come back and do it again. And I actually was concerned. I deleted them. They had a very regular pattern, and I was able, and they came in big bursts. I have not yet set up any kind of automatic filtering because I was so eager to delete them that I forgot to keep a sample of the style of the spam in order to filter them out. Fortunately, just this morning, 2 more showed up. Only 2. I'm not sure why. and they all have this this form. The interesting thing is they must be coming in through the derived work button, because they're taking the names of existing haikus now and slapping some random string on the end and injecting an URL for the text body. Anyways, now that I have a sample, I may filter for them, but if any of you have any idea why we're suddenly receiving a flood of spam, I encourage you to reach out to me. But the other big fun one is that Kevin put out a challenge to implement the maritime signal flags. And lo and behold, from the Czech Republic, we have gotten someone who has gone through and done them all. And let's slowly load here. And I'm going to let you take a look at a sample of them. Several interesting things about them. They're actually incredibly nicely done. Let me look at this one, because you'll notice that they're actually nicely minimal. Like, you can't read that at all. Well, no, this is John's derived from the other, and actually I'm going to talk about something about this one, so it's a good one to have chosen. So John made some minimal revision of it, but you'll notice that he's carefully factored it into words for left and top and bottom, and he's combined them nicely. John made an interesting addition, which is he made this portion gray, but something that's something that I'll point out in a moment is that there's an even better way to fix that. Let's look at another one. Oops. Let's do this one. And again, it's like they're marvelously factored. One-line definitions. He's built up his own XOR because there isn't one built in, and then he's got bars that he does carefully with a mod function, and then he XORs them together to get the checkered pattern. Great stuff. So two things. One, as you mentioned, John came through and added a gray region here. But the interesting thing is that the hold on. What he effectively accomplished is he's matched the background color, but as I mentioned last time, you have a fourth primary that you have the option of doing. You can do the alpha value to get transparency. So if I were to say change the background color, you can avoid lining up with it. And so in an example of creating derived works here, I lifted something that I've done from the. So we did these with the flags that Ting did a long time ago, and what's great about it is this is a wonderful example of how you can just stick a little something on the front and back. In fact, I've marked it out carefully here. This little thing in the front adds the waving, and then there's a little done stanza that needs to happen at the end to clip out the flag. And I've done this only for a few of them, but you can inject that. Now, where this gets interesting is, and let's see, let me go. So this is a version of that able flag again, and hopefully the movement will. You won't be able to see this on the screen. If you look very carefully, and you cannot see this at all in the projector, there's a thin boundary right there because it's gray, but it's not exact. You can see it. All right. However, okay. Yeah. If you hadn't pointed it out. If I hadn't pointed it out, right. I can't see it. But in this version, and I didn't actually, I assumed that John had done I didn't look carefully and assumed John had added the alpha. But in fact, oops, not that. What am I doing here? So you'll see that this version, oops, where's this version? Yeah, plus waving plus alpha lacks that. And the reason is that I've made a slight modification here. to the actual haiku. Where before he was producing, he was carefully providing gray for that region and doing half. I have instead simply duplicated the blue channel an extra time to provide an alpha channel so that there's a mask around it that cuts it out. And so if you're looking for transparency in your haikus, I encourage you to explore adding that fourth value in the stack. Beyond the email chain, Kevin, were you able to reach out to this Daniel Connolly fellow at all?
He's actually a known person.
He's a known person.
In fact, he's coming to Fort Bay in November.
Excellent.
Should there be one?
Should there be one? Indeed.
So in order to redeem my pledge to buy a lunch, I feel now obligated to have Fort Day.
Indeed, indeed. So anyways, exciting stuff. And if you have an idea for a new challenge, I encourage you to forward that along to Kevin, and we can offer up another challenge. I've been.
If I may stand in your proximity.
Indeed.
Well, don't touch the microphone because that would be wrong. I'd like to promote this on comp.lang.forth, and I need a cleverer challenge than my feeble-minded one. If you can think of something that may be not too daunting for somebody that's just getting started with this, that has elements of maybe motion, gradients, geometric figures, stuff, send me an email, and we'll formulate a challenge for those on comp.lang.forth and try to get them interested in fourth haiku. Thank you.
And I will endeavor to keep the spam at bay. In fact, I'll probably go and delete the two additional items of spam after having carefully logged their contents. Thank you all.
And I believe we're going to lunch. So this will end, and we'll see you in the afternoon.